So now we're going to have a series of contributed talk from people that submitted to the workshop. So happy to welcome, I guess you're just Mir's Dean,
yes,
right?
Yes, yep.
All right. So the floor is yours. You can present.
Cool. Thank you all so much. Really excited to be here. Tough act to follow after the last talk, but I'll do my best. So yeah, hi everyone. My name's Josh Myers-Dean. And I will be presenting our work on hierarchical semantic segmentation with autoregressive language modeling, or Halloumi for short. And yeah, this is a joint project with Adobe Research, UT Austin, and University of Colorado Boulder. And so while this crowd probably doesn't need much convincing, the big picture is that pixel level understanding is essential for many tasks such as segmentation, depth estimation, and scene parsing, which all rely on fine-grained spatial reasoning at the pixel level. But however, most paradigms these days stop understanding at the object level. They don't go deeper to like parts or subparts. And so that's where hierarchical semantic segmentation comes in. It's a realization that objects are not just flat structures. They're made up of parts and subparts. For example, you have a van. The van's gonna have wheels, to have windows, to have a body, and then those parts are gonna have their own parts that we'll refer to as subparts. And yeah, so to truly understand these things, we argue that models should be able to reason deeper beyond the object level. And so why does this actually matter, right? It's interesting, I think, as a research question, but practically, my main motivation comes for accessibility. You could imagine if you're able to actually ground evidence in an image, you could produce richer descriptions for people who are blind or low vision. But then also more practically in the manufacturing world, for like error detection, you might want to understand how fine-grained parts fit together to form a final structure, especially in error detection. However, all existing models that are capable of performing hierarchical segmentation face one of two limitations. First, they might need multiple inference passes, such as this great work Yifei, really good, but you have to prompt separately for the objects and then for parts. Or you need multiple decoders, which don't allow us to scale to deeper or coarser granularities. We're stuck at the granularities that we're trained on, or we have to make architectural changes in order to go deeper or higher. And yeah, so these approaches don't scale well to deeper hierarchies or even diverse objects in some cases. And so our solution, Halloumi, is we build off GLAM, which is, I think, my favorite work of the past 2 years, especially with the code base. But our approach, kind of at its core, provides a hierarchy in a single inference pass. We don't rely on specialized decoders need multiple inference passes. We instead reframe hierarchical semantic segmentation as a language modeling task, such that we can use autoregression. And then to actually get the segmentations, we leverage special seg tokens in the model's vocabulary that get fed into a decoder, and then we get segmentations in return, which works pretty well. And so Halloumi, the main contribution, there's 3 main contributions. So first, like I said, we reframe hierarchical segmentation as grounded captioning, such that now, instead of having to prompt different decoders to give us objects, parts, and subparts, we simply just give a caption that describes the hierarchy and ground those all in parallel. And while these captions sound awkward, like as humans, we typically describe scenes with respect to their intrinsics, lighting and stuff. They're a really good proxy to allow us to get a full hierarchy in one pass. Second, we introduce special tokens to the model's vocabulary that tell the model when to start and stop decomposing an entity, such that, as the van we saw earlier, and also children tokens that allow us to relay children entities to their parents. And that means that we could recover the full hierarchy as a post-processing step without relying on any heuristics. The model is actually learning this hierarchy. And while we inherit this advantage from GLAM, contrasting existing approaches, we only rely on a single mass decoder. Like I said, we don't need a specialized one for objects or for parts or for subparts. We just have one pixel decoder, and then the caption takes care of that granularity for us. As far as training, kind of line of status quo, we use LoRa as GPU poor folk do. So we tune about 5% of the parameters, and it trains pretty quick. And then we fine tune on the spin dataset, which our group introduced last year, which is the first dataset with subpart annotations and natural images. Some synthetic stuff exists, but this is the first for natural images, and allows us to go down to the subpart level. As far as performance, Halloumi is pretty good. We across all granularities, but particularly at the subpart granularity, since spin's a new data set, there's not many methods to benchmark, but for the ones that are out there, we see a considerable performance increase. We do fall a bit behind partly in terms of parts, but they do train on quite a bit more data than we do. So I'm happy with that performance for now. And going into like kind of the secret sauce of what makes our method work, first we analyze the impact of the hierarchical tokens, so those D and C tokens on the actual performance. And we find that not only does it increase subpart and part performance, but we also get better recall. So we're able to actually discover these subparts with reader accuracy. And then seeing, which granularity benefits from most data. Not really surprised to me, but yes, subparts, the more data that we use in our train set, the better performance we get, while objects and parts tend to saturate a lot quicker. Yeah, so for future work, I would love to see more hierarchical segmentation data sets so that we can support training and downstream applications, especially in multi-object scenarios. SPIN, while great, is inherited from ImageNet and part ImageNet, which focuses on a single object per image. And so to be truly useful, we'd like to see more dense scenes. Also decoding efficiency, I think, the language modeling community does a really good job of this. But that's kind of the bottleneck in our approach. Since we're autoregressive, we can't do the generation in parallel too well. And yeah, thank you so much. It's great to be here.
Thank you so much. We will group the question with the next one. So the next presenter is show or tell.
Show or tell.
Yes. Yeah, that one.
Oh, yeah.
Cool. All right. And you will have also the association to interact with the speakers. So I'm introducing Gabriele Rosi. You can take the floor now.
Thank you. So hi everyone, I'm Gabriele Rosi, a PhD student at Politecnico di Torino and Focus AI. And today I'm going to present our work, Show or Tell, a benchmark to evaluate visual and textual prompt in semantic segmentation. So before going into the details, I want to explain a bit the motivation. So in recent years, when you want to perform semantic segmentation, very often you use textual prompts. So for example, in open vocabulary models, you just specify a list of class, so car, trees, etc. And the models, what does segment is specified by this list of classes. But textual prompt has sometimes problems because it can contain misleading words. For example, mouse, if you see in the image we have below, if you just say mouse, it can be the electronic mouse or the animal. And sometimes also only text could be misleading. So it could be difficult to describe things that are, I don't know, like crack on the wall or something else. So textual prompt has some problems. So in recent years, there are plenty of research that employs visual prompts. So visual prompts are, let's say, masks or that specify some object by providing the models a visual example. So you can just draw a mask around an object, or you just give the model an image, and the model what tries to do is, okay, let's segment the things that are contained in the visual prompt. So as you can see here, telling the model that we want to segment exactly the animal, the model segments the animal. But what another problem that we can have with visual prompt is that they have problems with the appearance. So if you give the wrong visual prompt, the model does not understand quite well what to segment. So at this point, we discovered that there are no direct comparison between these two types of prompt in semantic segmentation. And so what we want to do is to develop a benchmark, sometimes something to understand which kind of prompt, so between the textual prompt and the visual prompt, works better for semantic segmentation. And so to do this, we developed this benchmark that compares directly the two modalities in order to understand which is better. And to do so, we just evaluate a bunch of open vocabulary methods and a bunch of visual prompt reference method on challenging dataset for semantic segmentation. So our benchmark, which is called Show or Tell, is composed basically by 14 datasets that you can see here in the image. There are very famous datasets, for example, ADI, Pascal Voc, or Cityscapes. But there are also more challenging datasets like PIDRAY, which contains X-ray images, or, for example, trash or pizza. And this diversity, this high variety of dataset can help us in order to understand better which of the two prompts work better. To test, in our benchmark, we tested 9 different methods. So we tested 5 open vocabulary semantic segmentation methods from the latest SOTA performance. And then we tested also 4 visual reference prompt methods that has been adapted in order to produce a segmentation for all the classes in an image, because very often these methods are used in a binary classification, in a binary segmentation way. So you just specify a class and they output that specific class. So you need to do a little adaptation to say, okay, we have this amount of classes, and we want to segment all of classes that you can find in an image without any prior knowledge in an image. So let's talk about the result. Here I have reported a limited, let's say a shrink version of the results. And as you can see here in the green square, up in the upper part of the table, you have open vocabulary methods. In the lower part of the table, you have visual reference prompt methods. So here you can see that in common scenes and urban environments, textual prompt still wins. So still the performance of textual prompts are better with respect to visual prompt. For example, click denoiser achieves 62, and the best performing methods among the visual prompt one achieve only 45. But when you move to more challenging data sets, so for example, toolkits or LoveDA or HouseParse, here the performance changes and visual prompt performed really well. So for example, you can see that on toolkit dataset, visual prompt methods achieve 88, while the best performing open vocabulary methods achieve only 12. And also on pizza, you can see that visual prompt methods achieve 62. But in general, doing an average of among all our data set, you can see that the best performing method among the textual prompts achieve only 27, while the best performing methods among the visual prompt one achieve 38. So the gap is really huge. However, as I said at the beginning, visual prompts still have some problems. So here, during our experiment, we just use 5 different seeds because we randomly sampled visual prompts. So as you can see here, choosing the right prompts could lead to a higher result or to lower results. And as you can see here in the 2 square, for example, on the pizza dataset with GFSAM, you can achieve 51.6, but there is a standard deviation of 14. So visual prompts are very, very sensitive to prompt selection. So these are the results. I will conclude my talk. So if you want to look at the paper, you can scan the QR code, and also the code is available on GitHub. And I want also to say that this work has been carried out with Focus AI, which is a local startup in Turin. And if you want to know more about this startup, you can visit us at booth 1228, and the CEO and CTO will be happy to share what we do in this startup. So thank you.
Thank you. So now we're having the speaker for STPro. Yes, I thought it was you, but I was not seeing you moving. Right. Okay. So that's gonna conclude the series of contributed talk. So you're Aaryan Garg, sorry, and you have the floor now.
Thank you. Can you guys hear me fine? Okay. I'm Aaryan, and I'll be presenting our work STPro, which is spatial and temporal progressive learning for weakly supervised spatio-temporal video grounding. So slightly different from the other talks, but this was a joint collaboration between myself from BITS and Akash, Kumar, and Dr. Rawat from the CRCV lab at UCF. So to give a bit of background, STVG involves open world free form grounding, which basically means that you're given an untrimmed video from a real world scene. You're given any caption. The caption does not have any fixed structure or fixed form. And you're expected to ground both the person or object being talked about in the caption, as well as the specific temporal subpart of the video that is being referred to by the caption. So you can see that the man is actually present in most of the video, but we only ground him for the parts where he does certain actions. So shouldn't vision language models or VLMs easily solve STVG? After all, it's just a combination of referring expression comprehension, which they're already very good at, and some action recognition. So for our trivial adaptation, we wanted to see if VLMs could do both the spatial and temporal work just through some kind of confidence score thresholding. So we would take the video and the caption as input to some VLM, let's say grounding dino. We'd get detections and some confidence scores. We'd threshold the confidence scores so we can remove the spurious detections. We'd add a tracking module so that we get actual spatio-temporal tubelets. And we take the one which had the highest average confidence score as our prediction. But yeah, which VLM should we even extend to this task, or which can we extend to this task? On one hand, we had multimodal LLMs like Florence 2, which can solve a bunch of different tasks. And on the other hand, you have task-specific VLMs like grounding dino that just solve one task really well. So for our adaptation, we actually wanted those confidence scores so we could do thresholding. And also, if we wanted a downstream adaptation later with the detections that we already had, then we wanted to have the localized features corresponding to each detection. So for those reasons, we chose to go with task-specific VLMs. And in our case, since we had the best performance on referring expression comprehension on grounding dino, we went ahead with that model. So you can see that just as a detection task, if you give just the classes to grounding dino, it does a pretty good job of grounding the relevant people, even in pretty complex scenes. But when you give it the actual caption that you're trying to ground, then it doesn't do as good of a job. So you can see that the actual ground truth is in green, but when we give the phrase as it is, we end up grounding the other person in the video. So the results of that trivial adaptation are that compared to some older work, we actually do pretty decently, but compared to more recent work, we're very far behind. So, what's troubling this zero-shot adaptation? Well, one issue is that confidence score thresholding isn't enough for removing the spurious temporal detections. And the tracking module that we use out of the box doesn't incorporate semantic context, which means that you end up grounding the person in question for as long as you can see them in the video. On the other hand, on the spatial side, if you look at the confidence scores of every detection in the tubelet, you see that there's very high variance, which means we're not confident about our spatial predictions. So what do we do about this? We thought that we'd add a dedicated temporal and spatial module. So we start off with the same flow from before, where we generate the proposals, and we add this temporal module that is just responsible for predicting a start and end timestamp corresponding to the caption. And then we use that temporal prediction to actually filter out those tubelets that aren't temporally relevant. And then based on that temporal prediction and the corresponding tubelets that we selected, we add a spatial module that just selects one of those tubelets out of all the available tubelets. And both the temporal referral module and the spatial referral module are trained weakly supervised because it's cheap. The results of this adaptation are that we actually see a nearly 5% increase in performance on both vidSTG declarative, which is a larger data set, and HCSTVG. But when we compare it to the upper bound that we have from the same detections from grounding dino, we actually see a 3 or 4x increase. That means our performance is really not great. So we still have a long way to go. So what's limiting this new adaptation and how can we improve it? Sorry. Yeah, so one thing we found on the temporal side, I think. Okay, I'm just going to proceed. So yeah, on the temporal side, if you give it a complex caption that has multiple different actions, we get an initial prediction that is kind of similar to the ground truth. But we wanted to see what happens if you take that last part of the caption where you have one action and looks at the man in red, and you actually remove it from the caption. What happens to the temporal prediction now? So you would think that if you remove an action, then the temporal prediction should shift to the left. But in actuality, we see that it shifts to the right. And when we expand this to the entire data set, we actually see this happen in more than 50% of samples, which means our model really doesn't get these action combinations. So what's an easy way to solve that? Well, take the caption that you want to train on, which has 3 different actions, and break it down into individual actions and start by training your model there. Then in the next stage, make it 2 action combinations, but make sure that those action combinations are continuous. You want to make sure that you don't skip over intermediate actions, because then effectively you're really not telling your model what the action is. So you want to repeat this until you arrive at the overall caption, and that's a summary of trying to learn composition one step at a time temporally. And on the spatial side, I think this is common in a lot of detectors. As the number of people in the scene increase, your ability to localize the right person as well as the right attribute start to deteriorate. And for example, in the first scene, we get the woman in white, but in the last scene where we want to ground a woman in brown, we actually ground a man. So yeah, how do we solve this? So the issue is that our spatial model actually needs to learn to ground both class and attribute at the same time. But why don't we let our model just learn to ground one thing, which is the attribute? So we have a mechanism called soft label filtering, where we leverage the predicted soft labels from grounding dyno to actually remove those tubelets which aren't relevant to the subject that we're trying to ground. So in this case, the center tublet is actually corresponding to a man. It might be a bit difficult to see. And through soft label filtering, we remove that tublet so that when our model now in training time tries to do grounding, it can focus mainly on the attribute and learn attribute disambiguation. Our main curriculum, we call congested guided sampling. And the idea here is that although detection features are very actor specific, they also have an influence of the background, and you want to mitigate that background influence while you're learning to ground the attribute. So we move from scenes where you have a lot of people in the same background to scenes where you have different people in different backgrounds. And just in the interest of time, I'm going to skip over exactly how we do that, but if you're interested, we can come back to that. So do the curriculums really help? Well, in this, we try to capture what happens when both the spatial and temporal complexity increase independently. So on the left, we have the temporal complexity in terms of number of actions increasing, and we see that our performance actually improves. And on the right, we have the spatial complexity in terms of number of actors increasing, and we see that, again, our performance actually does improve. Yeah, these are some qualitative examples. In this case, our initial PRG's prediction by the bar below the frames, like our temporal prediction is already really good, but we ground the incorrect person. And with STPro, we are actually able to retain that temporal prediction and get the right person grounded as well. And on the temporal side, TRG's initial prediction for this particular case was really bad. And as a result, the spatial prediction is also bad. And with the improved temporal prediction, we also ground the correct person. So yeah, this is a summary of our work where we are able to adapt VLMs to STVG. And we were the first work that incorporated spatio-temporal curriculum learning framework to solve STVG. And yeah, I just want to end by saying that my collaborator on this work, Akash, without whom this could have been possible, is available on the job market. He's almost done with his PhD, and I'm just about to finish my undergraduate degree as well. So I'm always looking for more research opportunities or any other opportunities. Yeah, thank you.
Thanks. If all the speakers can come here, and we have time for 1 or 2 short questions. Is there any question around? Otherwise, we will have opportunity to interact. All right. I see no question. I have one question for paper number 2. Just how much of your finding do you think extrapolate to other sort of segmentation? I mean, you're looking at semantic segmentation, but there are other types of segmentation, like materials, could be texture, all this kind of thing. Do you think it also extrapolate to that one?
You mean by
like the benchmark of textual versus visual?
Yeah, I didn't get so much the question. Sorry.
Sorry, I meant, do you think that your findings on saying like having a number of visuals can be better is also extrapolating to other tasks, like, for example, material segmentation?
Yeah, I think so, because with visual prompt, we are able to also specify basically if you have a good chair, probably it's with a visual prompt, it's better could be better to could lead to better segmentation, while probably with text could, I don't know. Actually, we didn't test so much with material and other stuff, but in my opinion, maybe could work better with visual prompt with respect to textual prompt, but we need to test it out.
All right, I mean, the purpose of that question is that it's heavily failing in that situation with text usually. So maybe it could be an interesting setup for you.
Thank you.
Cool. Is there a question from the audience? All right, then we can maybe go to the poster session. You can still interact with the people here. Please do, it's the right timing. We will resume the workshop at 4 p.m. with a keynote and then a panel session and the awards announcement. Thank you all.
Were there poster numbers somewhere that I